acetal from a hemiacetal. But that doesn't mean that every time we do a reaction to form a hemiacetal that we are like fighting against this, right? So yeah, formation of acetals. So the OH place can't be displaced directly by nucleophiles. That guy. So this is only going to be acid catalyzed, right? And we remember when we're talking about like SN1, SN2, this doesn't really count as a leaving group, right? Right? Is that OH is not a good enough leaving group? Is that correct? I want to say that's correct. Okay, cool. Yeah, so the same thing kind of goes here. We're not just gonna be able to displace an OH. So, if we make a hemiacetal in base, we don't have to worry about making an acetal, right? We can stop at the hemiacetal, that's what we get. If we make it an acid, we can make it keep going, and we can get an acetal. And an acetal is just the name for this guy. It used to be a ketone or an aldehyde, and we added an alcohol. So now it's a geminal diether. Yeah. If you want to be descriptive about it, you could describe it as that. So, these guys are more stable than acetals, or than hemiacetals, and you can actually isolate these in pretty good yield, right? Hemiacetals usually not overly stable. Like, you can form them, but usually, I mean, you're gonna form them like in situ while you get towards something else or something. You have to mess with it. You can't usually isolate them. These guys you can totally isolate, and you can get pretty good yield. So, only acid catalyzed. Make sure that's still up. In this case, we are going to start from a hemiacetal, because that's why I wear a lot of black, so I drop things. All right, we're going to start at this already, a hemiacetal, because, well, getting to here from an aldehyde or ketone is, we just did that. So the only way you can, once you get one of these, now we're talking about acid catalyzed. Honestly, I'm trying to think if, I guess technically maybe you could try and base catalyze a hemiacetal and then change it to acid catalyzed to make it an acetal, but there's no reason you would do that. Like, I feel like you might be able to, but honestly, when you neutralized it, hemiacetals aren't that stable, so there's a chance that you would just reverse the reaction, and then when you added acid, do both steps acid catalyzed, but it doesn't really matter. Start with a hemiacetal, this guy. And we are going to do this. So we are acid catalyzed, which means we've got this going on. in here. Some of that. Okay, so what we're gonna do is we start here and we're gonna go, you know what if this guy got protonated? Is this like a reaction that's dying to happen? I mean, whatever, stuff gets protonated and deprotonated all the time, right? Like, if we had, did you guys talk about deuterium labeling things? So, you know what deuterium is? It is, if I say deuterated solvent for NMR, right? Deuterated solvents are, let's see, hydrogen, deuterium, tritium. These guys are neutral, the Mickey Mouse ears. So it's got a neutron in the nucleus with there. Basically, you can use deuterium. It's exactly the same as hydrogen, but like you can tell spectroscopically what it is. So you can label one of these, and that's how some of these, sometimes that's how mechanistic chemistry is figured out, right? Because like we can't watch all this happen, so we can draw how we think it's gonna happen, but you could probably draw several ways that something could happen. How do we figure out which one is the actual one? Somebody does an experiment where they start replacing things with, hydrogen is the easiest to label with deuterium, but you can label with like anything with like a radioactive isotope, right? Same thing, but there's similar neutrons, and so it's, where did my eraser go? So, if you had this, and you were like, oh, this is, I don't know, for some reason, this is my deuterated solvent, and you put some other stuff in there, that wouldn't stay deuterated for long, right? Because like, it's easy to get rid of, it's labile, so you probably have constant acid base happening anyway to replace this guy. Like, that's just sort of how, yeah. So, this is the thing that can happen. It doesn't really matter how much it wants to happen, because as long as this happens, chemistry can follow from there. And chemistry is also statistics. Words are hard. Okay. We're gonna do, this is gonna be a pain. Okay. Okay, they just drew it funny. I don't want to draw it how they drew it. I'm gonna draw this. It's fine. That, O, R, O, H, H, plus. There we go. We've got that. I keep looking at the wrong thing. Okay, so we do this, and this guy is called, and, okay, fine, we have H, O, R as well. This is that's an oxonium ion. There we go. That's somewhat legible. Ion. This is why I do this to myself, but. So for the next step, I'm just gonna redraw that guy instead of, I hate redrawing, but that's why I like long boards. So I don't have to do the weird thing where I go like onto the next board, but I have to snake or. So just keep in mind when you're doing mechanisms, like on a quiz or an exam or whatever, or if you're, the way you're taking notes right now, you definitely don't have to do a step and then redraw the products to that step. to do the next step. You just keep going forward. I'm just doing that for maximum clarity. H plus R. And now we have, sorry about that again. Now we're gonna do some stuff. So we made this guy into an all right leaving group, right? And if we can make that into an all right leaving group, then, well, I mean, which one would rather form two single bonds carbon to oxygen or a double bond carbon to oxygen? The double bond, right? So this guy can peace out and is like encouraged to, as long as that guy forms this. Actually, I'm gonna do that backwards. Not that it overly matters, but I think it might help. Because it's really not, I just wanna be clear, this guy doesn't peace out first, right? This lone pair is like, hey, what if instead of you being here at all, I had a nice double bond? Everybody likes a double bond. We're way more stable without you. You can just go away. So, not that it super matters, but I formed this before I kicked that off just because this doesn't just disappear on its own. I'm not going to be able to tell what order you draw it in, but for learning, I should do it in a way that makes the most sense. So, this is reversible, and really what I'm drawing is, well, kind of, it's not exactly right, this isn't exactly the reverse of, the reverse reaction of a hemiacetal, right? But it's kind of the same. Like, it's exactly the same thing, except we're kicking out this instead of this. We could just as easily protonate this, and then reform this and kick that off, right? It's just that if we did that, then I'd be showing you the reverse reaction of making a hemiacetal, right? Does that make sense? Yes? No? Okay. Sorry. Okay, so now what do we have after this? We've got this. Carbon. We've got, I'm gonna draw it up here. That. And this guy. Okay. This guy is a resonance stabilized cation. So we've got one lone pair here. And we can sort of go, hey, if I wanted to resonate, then I could probably just do this. And I could move the positive charge to the carbon. I mean, that's not going to be favored. Like, this one isn't, this one's favored, right? Not this. But this is a resonance stabilized cation. So, we have formed that. I guess I can do that. And, well, and we kicked off water, so H2O. Maybe I should staple these, then it would be like visually obvious if I was on the back or front of something, rather than just flipping these pages. Okay, so now we've got something that looks like, we've got a carbonyl. We've got something that we know how to do chemistry with, right? So now that we did all that to prepare our chemistry, let's just start over here, because that's getting, it's not going to fit anyway, so we might as well do this. And we're going to start with this, our resonance stabilized cation. And we're going to go, hey, what about that alcohol that we started with earlier? We started with protonated alcohol, but kind of used that up, but that gave us some alcohol. So let's bring that back. And that's going to be our nucleophile. Yes? Yes.
So if that's going to perform a nucleophilic attack on that carbon, wouldn't it have to be the other resonance form? Because doesn't the positive charge need to be on the carbon?
Yes, but
Or does it not matter?
It does, well, so as long as, if we draw it on this one, then we draw the attack,
Yeah.
and then we erase this, like we don't have to do anything. I just don't like doing that because, I don't know, to me, this guy's a technicality. Like, it's there, but how are you gonna draw this? You're gonna draw it like this, where you have all of the, like, the full octets and everything, because, I don't know. So, it works the same way as long as when I do the attack, we remember to do that.
Okay.
So, yeah. You can do it either way. I don't know. I hate the idea of having to do a resonance structure and then continue on with the mechanism. If it's easy to, chemists are inherently lazy. So I did that to show you, but I would never have done that in real life. There we go. That's my answer for everything. And messy, but that's just organic chemists. Okay, so we do that attack. We had a positive charge. It's clear that this is not connected to this, right? Okay, just making sure, because they're really running into each other. Okay, and then we end up with a whole lot of color coding. Hopefully this color coding is useful, because it keeps tripping me up. Okay, we've got that. We've got these guys, and I'm going to put our new bond down here because I feel like it. It's this, and it's got an R and an H, so it's positively charged. Yeah? So, we're nearly there. Like, your post-lecture slides are going to label this a protonated acetal. I mean, yeah, okay. It doesn't really need its own name, but yes, we have made an acetal that's just, like, the only step we have is deprotonating, right? So that's going to be with another, there we go. Another mole of, we'll draw it over here, R, and we're gonna go, hey, give me that proton, you don't need it anymore, and it's gonna go, all right, yeah, that's fine. I don't think I really need that anymore. You're right, good call. And we're gonna end up with ta-da! Should I drop the second thing? Yeah. Acetal. Yeah? That makes sense? Cool. So that's what the electrons are doing. What does the bench chemistry us doing. We are going to use alcohol as your solvent, right? And in that, I didn't do an R and an R prime because, man, I mean, you want to form an acetal that has two different alcohols. Honestly, what you're going to form is a huge mixture of some that have both of the two substitutions of the first one, some that have two substitutions of the second one, some that have what you want, and then if the carbonyl was symmetric in the first place, like we've got two methyl groups, that's all we've got. But if it wasn't symmetric in the first place, we've got the enantiomer of that, where we've got one of each substituted, but like also it would be a chiral center. So that would be a mess and nobody does that and it's not worth it. We're gonna use alcohol as the solvent, just that we've got all sorts of alcohol around, and we're going to dissolve either dry HCl, which HCl, if it's dry, it's gas. And yes, it's kind of nerve-wracking to be in a room with an HCl gas container. I mean, I've never done anything with it, but our excimer laser has one. It uses HCl gas, so we've got a little gas cabinet, and it was a lot scarier when the HCl gas canister just didn't have a gas cabinet, and that room didn't used to be ventilated, and like, it shouldn't be leaking anywhere. It should just be going straight into the excimer laser and getting used up. But it's just sort of alarming to know that there was the idea that might not have been, what if something had happened? But now it's fine. It's in a gas cabinet, and that gas cabinet is a fume hood in itself, so we're good. So HCl gas into alcohol, or you can use p-toluene sulfonic acid in the alcohol. That's another thing you can do. Basically, large molar excess of alcohol pushes your equilibrium to favor the acetal formation. And of course it's reversible, so if you add like a bunch of water, you can undo both of those additions, both OR additions, and you can go all the way back to this guy if you want. If you pour a bunch of water in there. So, okay, had to figure out why this wasn't a non sequitur, sorry. The reason that we've got, so this is basically, if we've got water and alcohol together, they're miscible. Yeah, usually it depends, but like a lot of times we're using methanol or ethanol for this, or isopropanol. All of those are entirely miscible with water, so that's kind of annoying, but whatever. Because if it wasn't miscible with alcohol, then it'd be super easy, right? Because like, we would have alcohol, or we would have, whenever there's water formed, it would either like float on top or sink to the bottom. And usually it sinks to the bottom because, I don't know, most organic solvents are just not that dense, except for DCM, dichloromethane, methane. I don't know, most organic compounds are not as dense. So usually water sinks and you can just like drip it out the bottom and then you're helping push the equilibrium, right? But that's only if we're using, I don't know, like an alcohol that doesn't like to hang out with water at all. It's really not gonna separate fully. Like hexane will make that separate. Alcohol, So what we do is we make, so it makes an azeotrope. So an azeotrope is a liquid mixture of constant composition with a boiling point that's different from any of its components. Basically, they have this happening in a benzene layer. And we evaporate this, or we boil it, and then when it condenses over here, we've got hate this example because benzene doesn't have. Whatever. So an azeotrope is a thing where, like, if you were just trying to, basically we can't distill them apart. So an azeotrope is, and I guess benzene forms one with water, which is annoying. Alcohol and water will also form one. But basically, if you were just to try to distill them apart, you know, you do like a fractional distillation, and like one of them would come out and the other one would stay, or like something like that, right? But in this case, when you form an azeotrope, you're gonna get a very specific mixture, and that's just, it's just gonna keep going, and you're never gonna get those completely separated. So, or at least not just from doing a quick, like, normal, you know, you can't just hope that everything that evaporates is just the benzene because it forms this azeotrope. So it brings 9% water with it. So down here, you can't just collect the end result that you want, but once it condenses, you get this separation. And then